Today I'm going to discuss stiffness definition. So from Hooke's law, we have force equals stiffness per spring constant times the displacement. So K is the spring constant or spring stiffness and S is the displacement. So in matrix form, we can write this as F equals stiffness matrix times the displacement matrix. So replacing S by U, which represents the global displacements, F here is a vector of forces, so we have F1 and F2 equals K11, K12, K21, K22 times U1, U1, U2. So Kij are called stiffness influence coefficients. If U1 is equal to 1 and U2 is 0, then K11 is the force at point 1 corresponding to a unit displacement at point 1 and only at point 1. So we have to apply a unit displacement at each node, one at a time. K21 is the force at point 2 corresponding to a unit displacement at point 1 only. That's the meaning of this stiffness. K21 is the force at 2 corresponding to unit displacement at 1 only. K22 is the force at 2 corresponding to unit displacement at 2 only. So in general, Kij is the force at point I corresponding to a unit displacement at j and only at j. Consider the problem below with 3 degrees of freedom, 1 at each node. So if we draw the free body diagram of each node, and this is the force F1, and that will be in equilibrium if a force which acts opposite to F1 equal to K1 times delta 1. So that is K1 times delta 1. Then by action-reaction, this is the element or member 1 with stiffness K1, then we have also K1 delta 1 to the right. Then to maintain equilibrium of this member, then we have K1 delta 1 to the left. Then we draw the free body diagram of node 2, and this is equal to K1 delta 1 also. To maintain equilibrium of this node, we have K2 delta 1. So that's K1 delta 1, and the force to the left is K2 delta 1. So this is the free body diagram of this element here. And we have node 3. The force at 3 is, we will call it F sub 3 to the right. So we introduce a unit displacement. So supposedly the force here, which is supposedly to the left, is K2 delta 1. But it is, this is supposedly K2 delta 2, but because delta 2 is 0, so there's no force acting at this node here. So after we introduce a unit displacement at node 1 only, then F1 by equilibrium, F1 equals K1 delta 1, and because delta 1 is equal to 1, then F1 equals K1, and K1 is actually K11. So to maintain equilibrium at node 1, F1 to the right equals K1 delta 1 to the left, and because delta 1 is equal to 1, then F1 equals K1, and actually K1 is equal to K11 because that's the force at node 1 corresponding to a unit displacement at node 1 or point 1. So F1 equals K1 delta 1. Delta 1 is equal to 1, so F1 equals K1, and K1 is actually K11. The meaning of K11 is it's the force at 1 corresponding to a unit displacement at 1. So to maintain equilibrium at node 2, in this equation here, F2 equals K21 times delta 1, where K21 is the force at node 2 corresponding to a unit displacement of 1. But F2 equals K21 delta 1, and from this node here, F2 is equal to negative K1 delta 1 if you sum up forces horizontal and equate it to 0. So F2 equals F2 plus K1 delta 1 equals 0. So F2 equals negative K1 delta 1. And because delta 1 is equal to 1 at node 1, then F2 becomes negative K1. So therefore, we conclude that K21 equals negative K1. So since there are no displacements at nodes 2 and 3, there is no force in element 2. So if you look at this free body diagram of element 2 here, there are no forces because there is no displacement at node 2 as well as at node 3. So F3, which is equal to K31 equals 0. Again, 3 K3 is the force at node 3 corresponding to a unit displacement at 1. This is 0 because there is no displacement at 3, only at 1. And so if we draw this free body diagram of member 2, there will be no forces on this element. Next, we introduce a unit displacement at node 2. So we begin constructing free body diagram at node 2. So this is node 2. And this time, this force, which is opposite to F2, is K1 delta 2. The force here not shown, which is also to the left, is K2 delta 2 here. So there is also force here K2 delta 2. And equilibrium of member 2 or element 2, we have K3 delta 2 here, which is to the left. So that's K2 delta 2, K2 delta 2, and we also have K2 delta 2 at this end here. But there's no force going to the left at this node because there's no displacement at 3. So that's K2 delta 2 from by equilibrium of this element. So that's why the force here is also going to the left. So it is equal to K1 times delta 2, and by action-reaction, this is also K1 delta 2. So from the figure, F1 plus K1 delta 2 equals 0. So F1 equals negative K1 delta 2, but delta 2 is equal to 1. So F1 equals K1 times 1. So F1 equals negative K1 times 1. But K1 here is equal to K12. So drawing the matrix, we have F1, F2, F3. There are 3 forces. So K11, K12, K13, K21, K22, K23, K31, K32, K33. And we have displacement at node 2 only, which is 1. Then at 1 is 0. At 3 is 0. So the direct way of finding these stiffnesses is to expand this stiffness so that F1 equals K11 times 0, so K12 times 1. So therefore, it is equal to negative of K1 from this free body diagram here. F1 plus K1 delta 2 equals 0, so F1 equals negative K1. and that negative K1 is actually K12. Then F2 equals K22, K22, and it is equal to K1 plus K2 if you draw the free body diagram, or if you write static equation at this node here. F2 equals K1 delta 2 plus K2 delta 2, and because delta 2 equals 1, that's why F2 equals K22, and K22 equals K1 plus K2 from this free body diagram of that node. F3, on the other hand, is equal to K32, and K32 equals negative of K2 from, if we write static equation at this node here, F3 plus K2 delta 2 equals 0, so F3 is negative of K2, and that F3 is also equal to K32 if we consider this matrix and we expand that matrix there. So finally, when we introduce a unit displacement at node 3, so we begin drawing the free body diagram of node 3. Then this is K23. There is a force also going to the left, which is equal to K3 delta 3. So this is F2, free body diagram. And there's no force here because there's no displacement at 1. So that's F1. F1 therefore is 0 this time, which is equal to K13. So F1 equals K13. If you expand this, so F1 equals K13 times 1. But K13 equals 0 because there's no displacement at 1, only at 3. So there's no force here at this node, so F1 is 0. Likewise, F2 is equal to K23, and K23 is equal to negative of K2. So F2 equals K23 if you expand this matrix, and if you look at this free body diagram, F2 plus K2 delta 3 equals 0, so F2 equals negative K2 delta 3, and delta 3 is equal to 1, so that's why F2 equals negative K2, and in particular it is equal to K23. Then F3 is equal to K2 delta 3 plus K3 delta 3, and if we consider this expression here, F3 is equal to K2 delta 3, delta 3 is equal to 1, so F3 is equal to K2, and from this matrix here it is equal to K33 also if we expand row 3. So therefore, if we assemble the stiffness matrix for this bars here with only 2 members, if we assemble them, then we have the stiffness matrix for the entire system of bars, system of 2 bars, is equal to F1 when the displacement is 1 is K1, and this is negative of K1 from this result here, then 0 because F1 is 0 when delta 3 is 1. Then we have here negative K1, which is when delta 2 is 1. So F2 is equal to negative K1 from the preceding slide. Then K22 is equal to K1 plus K2. So that's why you have K1 plus K2 here. Then here F2 is equal to negative K2. Then when delta 1 is 1 at node 1, F3 is 0. In the second situation, when delta 2 is 0, F3 is negative K2, which is this, negative K2. And F3 is equal to K2 for the last case where delta 3 is equal to 1. So actually, you can expand this to any number of bars. And you look at the pattern here. We have K1, negative K1, 0, negative K1, K1 plus K2, negative K2, 0, negative K2, K2. Also notice that if you add the terms in each row, it will add up to 0. In each column also, it is also equal to 0. Diagonal, it's only in the diagonal where the sum of the stiffnesses is not 0. Take note of that situation. Or by superposition from delta 1 equals 1 and delta 2 equals delta 3 equals 0, if you expand this matrix here, you get F1, replace this by 1 here, then the 2 is 0, then F1 equals K11, and K11 is equal to K1 delta 1, and delta 1 is 1, so F1 equals K1. F2, on the other hand, is equal to K21, and it is equal to negative of K1 delta 1. Delta 1 is equal to 1, so that's why F2 equals negative K1. So it's here. F3 is 0 because the displacement is only at 1. From delta 2 equals 1, we have delta 1 equals delta 3, 0. Then we get F1 equals negative K1 delta 2 from the free body diagram also. F2 equals K1 plus K2 delta 2, and F3 equals negative K2 delta 2. So if delta 2 is 1, we get negative K1, K1 plus K2, negative K2. Then delta 3 is 1, and delta 1, delta 2, 0. So F1 equals K1 delta 3, K1 delta 1, and delta 1 is 0, so this is 0. F2 is negative K1 delta 2, negative K2 delta 2, so it is equal to negative K2, negative K2 delta 3 rather, so it is equal to negative K2, and F3 is equal to K2 delta 3. That's why when delta 3 is equal to 1, then F3 equals K2. That's it. I hope you can expand the matrix for any number of members. So in general, F1 equals K1 delta 1 minus K1 delta 2 plus 0 delta 3. F2 equals negative K1 delta 1 plus K1 plus K2 delta 2 minus K2 delta 3. F3 equals 0 delta 1 minus K2 delta 2 plus K2 delta 3. So in matrix form, we have F1, F2, F3 equals K1, negative K1, then 0, then negative K1, K1 plus K2, negative K2, then 0, negative K2, K2. And we have delta 1, delta 2, delta 3. Or F in general is equal to the force vector matrix is equal to the stiffness matrix or the global stiffness matrix for the system of bars times delta. If we solve for the displacement, then we have to invert the stiffness matrix and multiply it with the force matrix. So delta equals the inverse of the stiffness matrix times the force matrix. In order for a matrix to have an inverse, its determinant must be non-zero. Determinant of k is equal to k1 by expansion of minor, so k1 times the minor of k1, which is this 2 by 2 matrix here, then minus positive k1 minus negative of k1. The minor of negative k1 here would be negative k1, 0, negative k2, k2 here, then plus 0 because this is 0. So determinant of k is K1 times K1 K2 plus K2 square minus K2 square. So the product of this diagonal, K1 K2 plus K2 square minus K2 square, or minus negative K2 square. So this is it. Then plus K1 times negative K1 K2 minus 0, so negative K1 K2. So if you expand this determinant would be equal to K1 square K2 minus K1 square K2, which is equal to 0. Now, the reason why the result is 0, because remember, the bars have no restraints. So only when the bar has boundary conditions, for example, one end is a support or two ends are supports, that's the only time the bars will be in equilibrium. In this case, the bars will move because there are no supports or restraints. So therefore, there will be an infinite number of solutions to this case. Stiffness matrix is called singular because the determinant is 0. So this means that we have an infinite number of solutions to the equation. So this is so because no support and constraints given. Second reason, a lot of displaced configurations can occur. So it may be moving, it may accelerate or whatsoever. And 3, rigid body motion can occur. So once support conditions are introduced, then a unique solution will be possible as long as the structure is a stable one. So a support should be present to make the system to be in equilibrium. And therefore, there will now be a unique solution to the problem. So note that the stiffness matrix is symmetrical and has positive terms on the main diagonal. So have you noticed it? Positive terms on the main diagonal and symmetrical. So negative K1, negative K1, negative K2, negative K2. So it is symmetrical, 0, 0. So take note of that. This is always the case for a structure that is in equilibrium. So the reason why the terms in the main diagonal are positive because the displacement at the node requires positive force at that node. The terms in each column or row add up to 0. I already explained that earlier, that the sum of the column terms, horizontal terms, is 0. So I hope you have noticed it. Then individual element stiffness. So we now specifically set up the individual element stiffness in preparation for combining them for a bar with more than 2 elements. So consider the elements shown below. So this time we have this element here. The direction is, this is the origin. So let's say we have x to the right. That's force in the left node and force in the right node. This is the displacement at the left and the displacement at the right node. This element has 2 nodes and therefore 2 degrees of freedom, one on each end. So degrees of freedom is represented by its ability to be displaced. So we have UL and UR as the degrees of freedom. So FL, FR equals K11, K12, K21, K22 of UL, UR. So when UL is equal to 1, just like before, then, and UR is 0, then K11 FL equals K11 equals K1. And secondly, FR equals K21 times 1, so it is K21 FR. When UR equals 1 and UL is 0, then FL equals K12 and FR equals K22 for that case. So from basic mechanics of materials, we have deflection equals force length over AE, or in this case, FL over AE. Therefore, F is equal to AE over L times delta. Therefore, the stiffness of a bar is represented by AE over L. So in matrix form, if delta equals UL equals 1, then that means that the force is equal to AE over L. So FL equals K11 equals AE over L if delta equals 1. Because FR is negative of FL by equilibrium, so FR is equal to negative AE over L, the stiffness is equal to K21. The elemental stiffness becomes K equals EA over L, negative AE over L, negative AE over L, then positive EA over L. So if you factor that out, that's EA over L times 1, negative 1, negative 1, 1. This is also a symmetrical square matrix. So the force displacement relationship for this one element bar or rod element becomes FL FR equals E over L 1, negative 1, negative 1, 1, then UL UR. The order of the forces and displacements must be maintained as left first, then right. It should be remembered. Next, we have the combination of element stiffnesses. Element stiffnesses, or we assemble the stiffness of the system. So, assuming there are 3 members, in this case, it may be 4. So, there are 4 nodes. So, 1, 2, 3, and 4. So, F1, F2, F3, F4. So, member 1, member 2, member 3. Member 1 or element 1 has properties E1, A1, and L1, assuming. Member 2 of element 2 has the properties E2, area 2, and L2, and in general, member I has properties EI, area I, and L sub I. So by letting K1 equals EI, area I over Li, we have the force displacement relationship for the various elements as follows. So for element 1, F11, F21 equals K1 times 1, negative 1, negative 1, 1, U1, U2. So this is 1, this is 2, or column 1, column 2, row 1, row 2. Element 2, it is 2, 2 to 3. So F22, F32 equals K2, 1, negative 1, negative 1, 1. And we have U2, U3. So this is column 2, column 3. And element 3, we have F33, F43 equals K3, 1, negative 1, negative 1, 1, U3, U4. So this is column 3, column 4, row 3, row 4. So F1 equals F11 from this equation here, and setting the value of U1 equals 1. So it is K11. F1 equals F11 equals K1. F2 equals F21 plus F22. F3 equals F32 plus F33. And F4 is simply F43. So the structural stiffness formulation can now be finalized. So we have F1, F2, F3, F4 equals K1, negative K1, 0, 0, negative K1, K1 plus K2, then negative K2, 0, 0, negative K2, K2 plus K3, negative K3, 0, 0, negative K3, K3. So also observe how this matrix is being expanded, and I hope it is very clear here. Then if there is another element 4, for example, then you add another column here, 0, 0, negative K4, then K3 plus K4, then negative K4 here, negative K4 here also. So that's how it is expanded. So we have columns 1 to 4 and rows 1 to 4. So remember that F1, F2, F3, and F4 are either reactions or nodal applied loads. Remember that case.